Okay, I'm glad to introduce Professor Pilkyung here. Professor Pilkyung is assistant professor at New York University, Shanghai, China. He got a PhD degree in Seoul National University. He's working on this Moire patterns and Moiré Superlattices very early. Actually, nowadays you can see Moire patterns are very popular, and they can introduce to many interesting physics phenomena, superconducting, magnetism, so many anomalous Hall effects, many interesting topics. And Professor Pilkyung worked on it very early and in the really pioneer workers in this area. Actually worked on it for almost 10 years already. So it's very nice to have Professor Moon to have a talk here about the graphene superlattices. Okay, please, the stage is yours, Professor Moon.
Yeah, thank you for inviting me here today, and yeah, glad to be in this honorable opportunity. My name is Pilkyung Moon, and I'm an assistant professor in the New York University Shanghai campus. And today I'll very briefly introduce the electronic structure engineering by superlattice. So this is an outline. In the first part, I'll very briefly introduce the electronic structure engineering by using periodicity, in addition to the electrostatic superlattice. Then I will move to Moire Superlattices, the concept and the various Moire Superlattices. Okay, so graphene is a single layer of graphene. It is a two-dimensional crystal of carbon atoms. Since crystal is a periodic array of atoms, we can design the physical properties by controlling either atomic species or periodicity. Controlling atomic species means if we want UV light, we can use gallium nitride. If we want lead light, we can use indium nitride. Periodicity means it does not mean it's not the only I'm sorry. Periodicity does not limited to the distance between neighboring atoms. It contains the symmetry and the concept of every three-dimensional spatial distribution. For example, carbon has many allotropes. Diamond has a three-dimensional structure. Graphene is a stack of two-dimensional atomic layers, and nanotube is a quasi one-dimensional structure. Such periodicity governs the physical properties of carbon allotropes. Some materials have a very long period, while some materials has a shorter period. There have been various approaches to control the physical properties by controlling the lattice period. For example, we can change the entire period by compressing the system. This has been used in a silicon germanium material in the Intel CPU almost 10 years ago. Or we can introduce an additional periodicity, either by etching or replacing atoms in a periodic way. As you can see, there appears an additional periodicity in addition to the original period of underlying lattice. Usually we apply, there are lots of ways to introduce the periodicity. For example, we can etch the atomic layer and remove the atoms. We can introduce the Moire superlattice period, but the drawback of this method is the active layer is damaged. Damaged layer does not give quite good physical property. For example, electron mobility is significantly lower than the pristine material. Another approach is to give spatially varying doping. This is doable, but it's quite difficult to control the exact period. So it's quite difficult to make exactly 50 nanometer period. It gives 40 nanometer, 60 nanometer, and large variation. Another most frequently used approach is to use patterned gate. By gating electrode, we can get a sharp potential near the gate. The drawback is, although the potential near the gate is very sharp, but it is blurred, degraded as it passes through the dielectric layer. Recently, one of my collaborators developed a method to etch the underlying dielectric layer. By doing this, we can apply a very sharp and strong potential to the active layer. For example, here the silicon oxide is etched by using plasma etching. We can make a one-dimensional structure or two-dimensional structure with any arbitrary symmetry. Then we put they put boron nitride and graphene. Boron nitride as an additional dielectric media. This gives very sharp superlattice boundary, and since the graphene is not damaged, it gives a very high mobility. Okay, so how the electronic structure looks like. This is the Brillouin zone and electronic structure of graphene. Graphene has a hexagonal Brillouin zone and has a Dirac cone, the linear dispersion at the corner of the Brillouin zone. It is theoretically predicted that if we apply one-dimensional periodic potential to graphene, then the graphene Dirac cone is deformed, anisotropically deformed. So as the normalized potential strength U0 increases, the velocity gradually decreases and even drops to zero, becomes flat at the potential of 4 pi. As potential increases, the main Dirac cone recovers its velocity, but again, it's flattened at 8 pi, 12 pi, and so on. Interestingly, we also get another side Dirac point at this strong potential. There have been a few previous research on a graphene one-dimensional superlattice. However, although they reported resistance oscillation by Fabry-Perot oscillation resonance and Van Hoff singularity, but there have been no report on anisotropic velocity, electron velocity, or flattening of Dirac points, or the mysterious side Dirac points. Well, in collaboration with the experimental group, we show that the resistance along the direction parallel to the period and perpendicular to the period are completely different. So the system has 3 different groups of Dirac point: the primary main Dirac point, and the side Dirac point, and the mini Dirac point, or sometimes we call it a satellite Dirac point. The fact that we get strong resistivity peak at 4 pi of RYY is the evidence of the flattening of primary Dirac point. Interestingly, although theory predict that the same flattening occurs at 8 pi, but we do not see such resistivity peak. This, I think, theoretically, this is the evidence of the emergence of side Dirac point. At potential strength of 4 pi, the only Dirac point at charge neutrality point is the primary Dirac point. So if this is flattened, the resistivity increases. But at 8 pi, the new side Dirac point emerges, so they provide an extra transport channel. So even though the primary Dirac point is flattened, as you can see from the dip in the RXX, but we do not see any peak in RYY. That's the the evidence of a side Dirac point. Okay, by the way, why we see such a scale-like pattern at electron density other than 0? This comes from the mini Dirac point. And although it is well known that the main Dirac point, primary Dirac point, is flattened and recovers and flattened with respect to the potential strength, but there has been no idea, no information on the secondary and first mini Dirac point, secondary, and the third mini Dirac point. I theoretically show that those satellite Dirac points are also flattened with respect to the potential strength, and they appear in a staggered. Say, if one Dirac point is flattened, another Dirac point is flattened at another chance, and so on. This gives the scale-like pattern in the RXX profile. Okay, so although one-dimensional structure is interesting, but due to the time limit, I'll move to the Moire Superlattices. The discovery of graphene and its cousins, hexagonal boron nitride, transition metal dichalcogenase, provides an excellent opportunity to condensed matter physics. These materials not only provide interesting properties by themselves, but also serve as a building block to make a new kind of superlattice. We can make, since this is a two-dimensional structure, the bonding along the inclined direction is very strong, while the bonding along the vertical direction is weak. So we can easily attach or detach the atomic layers. A huge variety of material properties can be obtained by controlling the atomic species and the stacking sequences. For example, a graphene sandwiched between hexagonal boron nitride will give different physical property from a graphene sandwiched between molybdenum disulfide. However, it should be noted that whenever we stack atomic layers in a vertical way, we get an extra order along the in-plane direction. Why this happens? Imagine what happens if we stack two layers of periodic pattern. If the two layers have the same period, then the overlaid image also has the same period. But if there is difference between the lattice period or lattice orientation, we get an extra periodicity, which we call a Moire interference pattern. The period of Moire interference pattern is much longer than the underlying lattice. The word Moire, the Moire pattern is nothing but the interference between two different periodicity. In acoustics, we can see many similar phenomena. For example, in acoustics, we call such phenomena a beat. In a spatial pattern, we call it a Moire pattern. We can easily find it in many macroscopic phenomena. For example, if we stack two rectangular lattices, we get the emergence of a Moire pattern, which is much longer than the underlying lattice period. The word Moire comes from a Arabic word, but it's later converted to French. They are mostly used in a fabric. It looks like a marble or watered pattern. And as you can see from this, even Peter the Great is wearing a sash made up from Moire fabric. So it must be a very trendy item at that time. We can get similar Moire pattern in a microscopic system. For example, by stacking two layers of graphene and slightly twisting them, we get a Moire interference pattern. The size of a Moire pattern varies with the rotation angle between the layers. This structure is called a twisted bilayer graphene, and this is one of the most famous Moire superlattices. The Moire pattern is not a hypothetical phenomena. We can actually measure and observe the Moire pattern by using scanning tunneling microscope. For example, here we see the rotation angle as rotation angle varies from 30 degrees to 1 degree. The Moire pattern observed in our STM image increases, and the Moire period increases up to 10 nanometer. This is very interesting property of Moire superlattice. The lattice constant of almost every conventional materials lies in a very short range, 0.1 nanometer to 1 nanometer. But the period of Moire pattern can be as long as 10 to or even 100 nanometer. So Moire superlattice provides a unique opportunity to explore physics far beyond the limit of conventional materials. I will show up this later. Okay, then how can we calculate the physical properties and electronic structures? The number of atoms in a Moire unit cell can be as much as even 10,000. So it's quite difficult to calculate the electronic structure by using density functional theory or tight binding method. So people developed an efficient and effective model to describe the electronic structure. Yeah, various groups developed different approaches, but the results are almost the same. The idea is, as you can see, the local configuration of Moire superlattice looks like the local configuration of non-rotated bilayer graphene. For example, the vertex of a unit cell looks like AA stacking, while the intermediate state looks like BA or AB stacking. Such non-rotated regular bilayer, we can get a Hamiltonian very easily. So what we need is to find an expression that mimic or represent the potential of these regular structure as a function of the position in the unit cell. So this is the form of the Hamiltonian. The diagonal component shows the intra-layer interaction of each graphene layer, and the off-diagonal term shows the interlayer interaction. Here, subscript AA and AB shows the subscript of sublattice of layer 1 and layer 2. You note is the coupling strength, which is an order of 0.1 electron volt. And G1m, G2m are reciprocal lattice vector of Moire superlattice, and R is the position in the unit cell. If we put R equals 0 to this equation, we get a simple structure. The off-diagonal term vanishes, and we get interlayer interaction of AA stacked bilayer graphene. If we put another R at this point, we get BA stacking, AB stacking, and so on. So this form clearly reproduces the interlayer interaction at each local configuration. Since we have 3 different terms in our interlayer interaction, the interlayer interaction makes one state in either layer interacts with 3 different states in another layer. The first term has a 0 wave vector component, and second term has G1m, third term has G1m, G2m. The interlayer interaction couples the states with the wave vector differ by that amount. In the right panel, I plot the schematic electronic structure. The orange and green line shows the monolayer banded structure of layer 1 and layer 2 respectively. You can see Dirac cone at energy 0. As you've learned in quantum mechanics, the interaction between 2 states becomes stronger as the coupling coefficients becomes larger, and also the energy difference between the 2 states becomes smaller. At most wave vectors, however, these three states have quite different energy from the layer 1 states. So they do not couple very effectively. This is the reason why at most wave vector of the electronic structure, the twisted bilayer graphene merely looks like the band structure of decoupled bilayer graphene. However, as specific wave vector, one state energy can be close to the states of another layer. In that case, they strongly couple and makes a band opening. Band opening, when band opening occurs, the electron density diverges and we get a Van Hoff singularity, which is important for optical property and transport property. So these points shows the feature, the unique feature of twisted bilayer graphene compared to the decoupled bilayers. Okay, we can get a little more insight on the band structure by comparing the electronic structure of two different rotation angles. In the upper layer, upper panel, I show the lattice structure of 22 degree and 5 degree. And below, I show the extended Brillouin zone of each structure. The orange and green hexagon shows the first Brillouin zone of each graphene layer. And there are Dirac cones at the corners. If we plot the band structure along this line, we can see the Dirac cone of layer 1, 2, layer 1, 2, and so on. Interestingly, so if we take a look at the interaction between these two Dirac cones, they show Dirac cone at these 2 points and makes a saddle point Van Hoff singularity at this point. Interestingly, as rotation angle decreases, the distance between these two Dirac cones becomes closer. As a result, the energy of this Van Hoff singularity moves closer to the energy 0. On the contrary, the interaction between these two Dirac cones make a Van Hoff singularity at higher energy. But the distance between these two Dirac cones becomes farther as the rotation angle decreases. So the energy of this Van Hoff singularity moves away from energy 0 as rotation angle decreases. Finally, these two Dirac cones belongs to the same layer, as you can see from the color of the line. So they are the different Dirac cone of the same lattice. So this is just the saddle point of monolayer graphene. So its energy must be almost independent to the rotation angle. The schematic illustration is consistent with my numerical calculation. Here I plot the density of state of twisted bilayer graphene by varying the rotation angle from 30 degree to 1 degree. As rotation angle decreases, the first Van Hoff singularity moves closer to energy 0, and the higher Van Hoff singularity moves away from energy 0, and the highest Van Hoff singularity stays almost the same energies as expected. The same is true for the optical spectrum. The lowest energy peak blue shift, middle energy peak red shift, and highest energy peak stays at almost the same energy as rotation angle increases. This is a purely theoretical prediction, and the experimental result was consistent with the theoretical prediction. Recently, I collaborated with a group in a University of Seoul, and they measured the optical spectrum by changing the Fermi energy and also changing the interlayer potential asymmetry. This provides many interesting property and the electronic structure near the Dirac point. However, if you are interested in, I usually do not recommend you to use twisted Moiré graphene as optoelectronic devices. This is because usually the strong absorption peak occurs between the transition between Van Hoff singularity. But I theoretically proved that the transition from first Van Hoff singularity to first Van Hoff singularity is completely forbidden by the lattice Hamiltonian. The first Van Hoff singularity in the hole side to the electron side. So this is the reason why we see dip in the absorption profile. Instead, the absorption peak occurs from the transition between Van Hoff singularity to normal bands. This means that half of the electron in a Van Hoff singularity does not work for the optical transition. But this is only for twisted Moiré graphene. And if we can find a much better suitable material, for example, that enhances the transition at the Van Hoff singularity, then such Moiré superlattice would be a very good candidate for electronic devices. It is interesting to see that the electronic structure of twisted Moiré graphene is quite similar to that of monolayer graphene. So we have a Dirac cone, Van Hoff singularity, and so on. But the energy scale of twisted Moiré graphene is much smaller than that of monolayer graphene. So we can easily access the Van Hoff singularity and even the next bands by charging the system. Here I plot the band structure of twisted Moiré graphene with 3 different rotation angles. The slope corresponds to the Fermi velocity of twisted Moiré graphene. As rotation angle decreases, the Fermi velocity gradually decreases and even drops to 0 at specific angle. This is a very interesting point. An electron in a single layer graphene can only have a single fixed velocity of 10 to the 6 meters per second. Electron can never change its velocity and never stops in a monolayer graphene. But by simply stacking 2 layers of graphene and slightly twisting them, we can change the velocity a lot and even stops the electron. So Moiré superlattice is an excellent candidate for band's way to engineer the electronic structure. Such a flat band structure gives very high electron density and many interesting correlated phenomena occurs. For example, in 2018, people in MIT reported the emergence of both insulating phase and superconducting phase. Since superconductivity is one of the many the ultimate goal of condensed matter physics, so people are now rushing to this magic angle twisted Moiré graphene. For example, I collaborated with a group in United States and Israel and measured the spatial variation of rotation angle. So by using squid on a tip, we can get the Landau level spectrum at each local structure. And the Landau level spectrum varies with the rotation angle between the twisted layer. So by comparing the observed spectrum with the theoretical calculation, we could get the spatial mapping of the rotation angle. So initially, people wondered why some magic angle structure shows superconductivity, while some structure doesn't. And we show that the device which does not show the superconductivity is almost disconnected. So there are high angle regions disconnecting the path from one gate to another gate. While the structure connected between the gates clearly shows the superconductivity. Okay, so twisted Moiré graphene is not the only Moiré superlattices. we can get any Moire phenomena by using the incommensurate stacking. For example, hexagonal boron nitride is isostructural to graphene, but there is 2% lattice mismatch between graphene and boron nitride. So whenever we stack graphene on top of boron nitride, we get the Moire pattern with the period bearing with the rotation angle. This is graphene on boron nitride. And the most important difference between twisted biographene and graphene and boron nitride is that the graphene boron nitride has emergence symmetry breaking. So the breaking between the A and B sublattice. So it gives a band opening at the primary and mini Dirac points. Theoretical prediction shows that the band opening at the hole side is almost 3 times the band opening in the electron side, and it is consistent with the actual experimental data. And also the emergence symmetry breaking makes the belly degeneracy lifted. So the K and K prime belly show different Landau-Level spectrum. And likewise, the emergence symmetry makes the magnetothermoelectric effect, Nernst effect, and it's prominent at the hole side, which gives a clear difference between K and K prime belly. Okay, so we can also see the Moire phenomena in a one-dimensional structure, such as carbon nanotube. Carbon nanotube is a single sheet of graphene rolled up into cylinders. The roll-up direction is called a chiral vector, and depending on the chiral vector, the nanotube shows different physical properties. Some shows metallic structure, some shows semiconducting structure. Here I plot the lattice configuration of a single-walled and double-walled nanotube. Although the difference between single and double is just the number of tubes, but this small difference makes the calculation of double-walled nanotube very challenging. This is because in a single-walled nanotube, we can always define an exact periodicity. So we can solve the Bloch equation and get the electronic structure. The situation becomes totally different in a double-walled nanotube. Here, the period of inner and outer tube usually do not match except for very few cases. So we cannot solve the very fundamental equation in condensed matter physics, the Bloch equation. This is the reason why, although almost 20 years passed since the first discovery of multi-walled carbon nanotubes, but very few is known about the physical property of incommensurate nanotubes. But we found that we can describe the electronic structure by using the Moire interference between the two tubes. We use the same strategy as two-dimensional family. The difference is that in a twisted biographene, we only have rotational freedom. In a graphene and boron nitride, we have isotropic expansion in addition to the rotational freedom. Double-walled nanotube is a little unique because it is composed of rotational freedom and uniaxial expansion. Why we get uniaxial expansion? This is because of the geometry of nanotube. Here I plot the cross-section of nanotubes, and it shows the atomic position of inner and outer tube. Since the dimension of inner and outer tube are different, but they must match when they return to the origin. So it works as if the system is dilated. However, please note that this is not an actual strain. So it does not give a vector potential, which comes from the actual strain. It just changed the relative position the matching of between the atoms. Anyway, such uniaxial expansion makes the Moire pattern very unique. It gives almost the scale-like one-dimensional pattern. Before our work, the most studies ignore the interaction between the tubes. So they use the decoupled features. So this is the band structure of two semiconducting nanotubes. They show some gap structure. But our calculation shows that in some structure, the intertube interaction is very efficient. Say it enhances it, so it even closed the gap. So we can get metallic structure by the combination of two semiconducting nanotubes. But please note that such a strong coupling occurs only when the chiral vector of inner and outer tube matches some condition. And this is the band structure of a conventional picture composed of a semiconducting nanotube and metallic nanotube. And we show that a specific configuration, the metallicity is completely removed, and we get Landau level-like spectrum, even in the absence of magnetic field. Recently, we show that the nanotube as strong coupling condition actually shows the extra peak, which is not present in a single decoupled bilayer picture. Okay, so that was the application and the fundamental part, application part. And how many? In the later part, I would like to very briefly introduce the Hofstadter's butterfly and quasi crystal. So Moiré Superlattices not only provides a valuable opportunity to band structure engineering and application, but also serves as a good test bed to study fundamental physics. I was very interested in what happens if we apply magnetic field to such an exceptionally large unit cell. We know that the Landau energy spectrum of each graphene layer evolves into a Landau level in a magnetic field, but there's been no idea how the energy spectrum of Moiré Superlattices looks like. This problem is interesting because it is at the cross between two very simple physical situations: an electron in periodic lattice and electron in uniform magnetic field. These two problems are very well understood. The electron in a periodic lattice shows a band structure with finite energy width, while electron in a magnetic field has discrete energy level, but they look almost incompatible. So it is very interesting to see how nature harmonizes the two at the cross point. In fact, this has been a topic of long debates and scientific inquiry since the early days of condensed matter physics. And people soon realized that something weird happens if we plot electron energy as a function of magnetic field. So it's not simple Landau level spectrum. It looks very weird. In 1976, Douglas Hofstadter calculated the energy spectrum in a hypothetical rectangular lattice. And this is the energy spectrum. The lateral axis is proportional to the magnetic field B, and vertical axis shows the electron energy. The black line shows the allowed energy at each magnetic field. A single vertical axis at magnetic field 0 shows the range between energy minimum and energy maximum of a single band. As magnetic field is turned on, infinitely many Landau levels emerge from the corner of the bands. However, as magnetic field further increases, each Landau level evolves into a very complicated tree-like structure. This spectrum is called Hofstadter's butterfly, since the shape of gap looks like a butterfly. This is attracted many interest because this is the first fractal phenomena predicted in condensed matter physics. That is, if we magnify a small portion of the spectrum, we get the spectrum similar to the original image, but with a much smaller energy scale. It continues again and again to infinite subgeneration structure, making the entire spectrum self-similar. However, it sounds very strange. The situation that an electron is under the simultaneous influence of a periodic potential and magnetic field is not unfamiliar to us. We've already seen this situation in many magnetotransport and magnetoabsorption spectrum, but we've never seen any butterfly there. This is because the Hofstadter's butterfly appears from the competition between two different length scales, and at general configuration, the two scales are completely different. The period of typical unit cell is an order of 0.1 nanometer, while magnetic length is an order of 10 nanometer. So suppose you ride a bicycle and hit a very small stone. If the size of your bike and the stone is very different, the coupling is almost negligible. If the size becomes comparable, then they effectively interact with each other. So can we measure the butterfly by simply increasing magnetic fields? To see the butterfly, we need almost 10,000 Tesla. How large is that? The Earth's magnet is an order of 10 to the minus 5 Tesla, and the rare Earth's magnet is an order of 1 Tesla. And with 1 Tesla, you can even levitate a pencil lead. But please don't try this at home, because if your finger is kept between the two magnets, you cannot remove it by hands. And with 10 Tesla, you can even levitate a frog. The best available magnet can reach 100 Tesla for continuous field, and even 700 Tesla for just a fraction of a second. This is because the magnetic field strength is the number of magnetic flux per given area. So if we can squeeze the magnetic field to a very narrow area, you can instantaneously increase the magnetic field. Of course, we can get much higher field. This is actual magnetic field experiment by explosive compression of the specimen. But even with 3,000 Tesla, you can only see a very small portion of the Hofstadter's butterfly, which merely looks like Landau level. So it is not feasible to see the butterfly by simply increasing magnetic fields. So we need a larger unit cell, but ordinary crystalline lattice has much smaller unit cell. So we introduced the Moiré Superlattices. Theoretically predicted that Moiré Superlattices will show Hofstadter's butterfly at moderate magnetic field. The spectrum of twisted violet graphene at rather large twist angle merely looks like Landau level because the unit cell is still too small. But if we decrease the rotation angle, the unit cell becomes larger and the spectrum evolves to fractal structure. You can see that at specific magnetic field, you get some band structure with finite energy width, even in the presence of magnetic field, and the Landau level spectrum at other magnetic field. And this is the answer to the original question, how nature harmonizes the Bloch quantization and Landau quantization. At specific magnetic field, which makes the magnetic length a rational multiple of unit cell length, then we get band structure. When the ratio is not rational number, we get Landau level structure. if we further decrease the rotation angle and increase the unit cell size, we can see the butterfly at much weaker magnetic field. And in collaboration with experimental group, we showed the fractal energy spectrum and the Hofstadter's butterfly. Okay, so that was the Hofstadter butterfly, and this is much newer results, quasi crystal. So far, most of the research have been focused on a low-angle twisted parallel graphene, which clearly shows long-range Moire period. However, we show that twisted parallel graphene at 30 degrees shows dodecagonal 12-fold quasi-crystalline symmetry. Quasi-crystal is a unique phase of matter which is ordered but not periodic. It is at the interface between periodic crystal and amorphous solid, so it can provide important insight into the effects of magnetic atomic ordering. We show that we can design the quasi-crystal by stacking atomic layers at a specific configuration. And I was a corresponding author of this paper. I developed a theoretical model that can calculate the electronic structure of such non-periodic structure. Usually, we can only calculate the electronic structure of periodic structure because only in that case we can solve Bloch equation. But this van der Waals quasi-crystal is very special, so we can even calculate the electronic structure very precisely. So we can get the band structure and the local density of states. Interesting point is that I show that in a low angle twisted parallel graphene, the majority of interaction is the two-wave mixing, the strong coupling between a state in a layer 1 and another state in layer 2. But I found that in this graphene quasi-crystal, there is a state where one state in layer 1 strongly and equally interacts with the two states in layer 2. And each of these two states also strongly interacts with the two states in layer 1. And then finally, these 12 states makes a resonance coupling. This is the feature unique to this quasi-crystalline configuration. So, and at other energies, the electrons, this is the real space electron distribution. At most other energies, electrons are uniformly distributed over the atomic sites. But the quasi-crystalline states are non-uniformly distributed and shows quasi-crystalline local density of states. And it's, we can easily expand this to three-dimensional structure, which sometimes called SLB twisted graphite. Such a structure is unique because it shows some interesting flat bands or the transition between type 1, type 2 wire fermion. But I also showed that such a structure can host quasi-crystalline resonance states with infinitely many states in a single system. Okay, so this is a conclusion. So Moiré Superlattices provides a unique opportunity to control the physical properties and design the electronic structure. And it also provides excellent opportunity to study the fundamental physical problems, such as Hofstadter's butterfly or quasi-crystals. So thank you for your attention.
Yes, thank you very much, and for the very beautiful pictures and beautiful talk. So this is theoretical talk. I never see a theoretical talk which is so beautiful together with the experiment. So any questions from the audience? Please feel free to ask. It doesn't matter which questions. So for the last part, maybe I just start. For the last part, for this quasi-crystal, for this resonance states, what's the experimental signature? How do you probe it in the experiment?
Actually, in this paper, in this paper, we measured the RPEX spectrum, which is completely different from periodic twisted graphene. But so I actually expected the local configuration, the quasi-crystalline distribution of electron. So this would be observable by using STM or other method. However, please note that they appear at a little larger, higher energy of 1.5 to 1.7. So it's a little challenging to access that range by charging method. However, I also showed, not in this paper, in the next paper, I showed we can use TMDC or other, even the rectangular layer. And for example, rectangular layer stacked at 45 degree gives octagonal A-fold rotational symmetric quasi-crystal. So by choosing a suitable material, we can make the quasi-crystalline states appears at a charge neutrality point. So although this would be very interesting, but this might not be, we cannot access that region in a twisted Moiré graphene, but similar feature will be observed in other TMDC and so on.
Yeah,
but
nice.
however, I'm sorry for interrupting.
Yes.
Yeah, I'm sorry for interrupting. The quasi-crystal is interesting because this is a non-periodic but uniform system. But the problem is that quasi-crystal once attracted much interest in early 90s, but people soon found that there is no application in a quasi-crystal. This is mathematically interesting, but has no physical application. So people all moved to in 2 years later, people moved to the superconductivity in late 90s, I guess.
Yeah, that's why not only from the energy, from this band structure, right? So whether it can lead to some interesting applications.
Right.
Yeah.
So it can provide the insights on a physical understanding, but not application at this point.
At this point, yeah. Okay, thanks. Justin, you want to?
Sure. Yeah, no, it's a very interesting talk. I actually had a quick question. So it's remarkable how you were able to solve the eigenenergies for these quasi crystals. What was your algorithm? Was it using some kind of higher dimensional system, and then you do you look at a crystal in a higher dimensional system, and then you project down to the lower dimension because of this old trick that says that, a quasi-crystal is basically a projected, higher dimensional crystal. Is that what it is, or is it something a bit more?
Almost similar. So I first expanded this to 4-dimensional structure and found that it was first expanded. So although this is 2-dimensional structure, but it has a 4-dimensional subspace. So I first found the subspace spanned by the Hamiltonian in a 4-dimensional space, but soon found that this can be reduced to 2-dimensional structure because of the specific, the unique situation of this, the 2-dimensional van der Waals quasi-crystal. As you know, you surely understand the higher dimensional system. The quasi-crystal, there are lots of definitions of quasi-crystal, but the most recent one is the system of which periodicity or the basis vector, number of basis vector larger than the dimension of the system. So this is 2-dimensional structure, but it has 4 independent vectors. So the subspace are spanned by 4 dimensions. However, I found that since each layer, so although the combination of 2 layers give 4 vectors, but each layer still has their own periodicity. So in this layer, the 2 other periodicity is observed by the periodicity of the crystal. And in this layer, the periodicity is observed by crystal. Of course, the observed part depends on the layer. Since layer 1 and layer 2 are different, they observe different part of the four-dimensional structure. So layer 1 expand the two-dimensional subspace, and layer 2 expand the two-dimensional space, but their space are different. This is the different part, different from the Moire Superlattices. In a Moire Superlattices, the subspace spanned by layer 1 and layer 2 share the same point in the reciprocal space. So they give periodic space in the reciprocal space. But in this quasi-crystal model, the subspace spanned by layer 1 does not same as the subspace spanned by layer 2. But still, we get the exact electronic structure. And it can also apply to, for example, other symmetry. For example, we can get the electronic structure of a rectangular layer and hexagonal layer.
Yeah.
So
yeah. No. Actually, that's very interesting, and it's quite clear. I had one question about that. So you know, is there an equivalent then, therefore, of band structure? So you know, am I able to draw some kind of band diagram? Is there some equivalent K, or is it just all completely localized, and so you don't actually have any notion of K anymore, and it's just gone? So what to what extent do you have that notion of K? To what? So you have these things KK prime there, right? But then what does that even mean in the case where you don't even have any true crystalline periodicity? Would you maybe have something about that?
Actually, this is the band structure of twist, the graphene quasi-crystal. And such a plot is possible because at most point, the two graphene layers are almost decoupled, and the strong interaction occurs as specific wave vector. Here I plot it as 0, and there the resonance coupling occurs. At other points, it smoothly varies to the decoupled structure. And the question on the physical meaning of wave vector is very important part. Actually, this is one of the most frequently asked questions when I present, but I didn't provide the presentation material. So the meaning of wave vector K is different in a layer, although this system shares a single wave vector K naught. So single states has described by single wave vector K naught. So layer 1 state, layer 2 states share the same wave vector. However, they share the same wave vector. So that's the reason why we can draw the band dispersion in terms of wave vector. However, their meaning in each layer are different. So K, although the K and K are same, their meaning in each layer are different because the period of each layer are different. Suppose you draw a sine wave with a K wave vector and plot the site with a different periodicity. So even though the wave itself is a continuous wave itself is same, but the actual phase of the site of layer 1 with a period of L1 and layer 2 with the period of L2 are different. So this is simple one-dimensional case. The situation becomes a little complicated when we consider two-dimensional structure. So even though we use a K, single K for each layer, but their physical meaning are different.
Okay, sure, yeah.
Yeah, so any other questions from the audience, from students especially? So you introduced this, I have another question, right? You introduced how to calculate this Moire patterns in the graphene. And so for the gate dependent, how heavy is the task for the gate dependent change of the band structures? Yeah.
You mean the early part, the gate electrostatic electrostatic superlattice?
No, for the normal, for example, for graphene, you have a Moire twist the angle. Then you can calculate this band structures. then by applying different gates, you will have a different band structure, right? So how heavy is this calculation task, and how do you do it?
Different gate. Usually does different gate potential gives different interlayer potential asymmetry. And the gate does not change the rotation angle between the layer, so the geometry itself is kept constant. But there will be difference in the layer 1, layer 2 on-site potential. That makes some change, like the light figure, the light panel. So the asymmetry potential effects, and also it gives some charging. But that's very, very easy to include in the calculation.
Okay. Yeah. So now you can see that with the twisted graphene, the superconducting is there, and ABC graphene is also there. How about the copper nanotube with double layers? Can you do some prediction of that as well? Is it possible?
Actually,
you have two
actually
copper nanotube?
the superconductivity is now very red ocean, so I try not to be involved. So I usually my main strength is the modeling in the single particle theory. So I developed describe the system by single particle theory, such as tight binding method, and try to make it this the effective theory, just as I did in a quasi crystal. So effective theory catches the very important part of the system, and I describe qualitatively describe the system. But the superconductivity and that part is now already moved to the many body correlated system. Is far beyond my usual interest.
Okay. Other questions? Also, please get this chance. So our students sometimes are too shy, you know.
Yeah. But if anyone are interested or have questions later, you can also send me an email. I will surely answer to the questions.
Yes, please. If not, let's thank Professor Moon again for the very wonderful talk. So
thank you very much.
And later on, we will go to a breakout room for some other discussions together with Justin, Abdullah, and one of my postdoc. Okay.
Yeah.
All right. So thanks very much. Thank you.
Thank you very much.
Are we using the same Zoom room, or are we going to go to a different?
I think we go to a breakout room. Your student will drag us there, or
Or